All right, so I want to talk a little bit about the mathematics of motion that was being developed in the time period under consideration. In particular, I want to talk about this law regarding constant acceleration. So, what this says, what this law says, is that if you're constantly accelerating over a certain amount of time, let's say from time 0 to time tf, so constant, I'll say constant acceleration from time 0 to time t sub f for a t final, then the distance that you go the distance traveled, or of course we're thinking about this like in one straight line, the distance you traveled is equal to 1/2 times, I'm going to do v sub f, meaning velocity final, times tf, which is the final time. In other words, the amount of time. That is the distance that you went. Now it's interesting, just kind of reading how they thought about these physical quantities. For example, it said that they defined velocity to be that part of motion which can be increased. I mean, it's just they thought about things a little bit differently than we do. The argument that I'm going to give here for this is by H'Berry. I think I'm not spelling that correctly. Let me see how it is spelled. Yeah, okay. Missing E. I don't spell a lot of things well. Now, I'm going to give the argument that he gave. To me, this argument is a little bit bizarre, and almost is sort of circular. And I'll explain what I mean when I get there. And after I say that, I want to maybe talk about two alternative ways of viewing this same rule here. Anyways, so let's say we've got 4 people running for an hour. So these bars here don't represent length, they represent time. So 0 to 60 minutes. And the first one is going to be me, Rob. And I have constant acceleration from, let's say, 0 feet per second over here to 8 feet per second after an hour. Okay, and then we're going to look at okay, so then we're going to look at Todd, and he is going constant 4 feet per second. You're going to have another person, KB, and she is going to, so for the first 30 minutes, she is going to accelerate constant from 4 to 8. So she'll accelerate from 4 to 8 in the first 30 minutes, and then, as we'll see, it doesn't matter what happens in the second 30 minutes. And then Allie, she is going to start off at 4 feet per second. The units don't matter. She's going to start off at 4 feet per second here, and constantly have a constant deceleration to 0 here. And again, it's not going to matter what happens for this time right here. Okay, so since I have constant acceleration, I'm accelerating constantly here. I mean, what that means is that in the middle, I'm also going to be at 4 feet per second. Okay, so here's how the reasoning goes. When I go, for the first 30 minutes, I'm accelerating from 0 to 4, but Allie is decelerating constantly from 4 to 0. So there's like a symmetry here. So the distance I travel during this period of time, let's call it L, is going to be equal to the distance that Allie travels in this time as well. Okay, we can kind of just think about like if we run, if you look at me, if you videotape me running or whatever, it's not videotape, but whatever, going from the first 30 minutes, accelerating from 0 to 4 feet per second. If you were to like play this tape in reverse, you're going to get the same distance as what Ali is doing here, just going from 4 to 0. So the distance here has to be equal to each other. Now my distance here that I go from the distance that I run going from the 30 minutes here to 60 minutes is clearly going to be this distance here, because KB has constant acceleration from 4 to 8. I have constant acceleration from 4 to 8, so we're going to go the same distance. So the total distance I run is equal to the distance that Ali goes in the first 30 minutes plus the distance that KB goes in the first 30 minutes. Okay, now here's the part that to me almost assumes exactly what is trying to be proven here. So what is next asserted is that if you look at what's happening with KB and Ali, KB, they both start at 4. She is increasing from 4 to 8, and she is decreasing from 4 to 0. So in other words, what's happening, like the total distance traveled by both of these people, the total distance traveled over the first 30 minutes by KB and Ali is like they're both would be the same as if they were both traveling at 4 for that entire time. Because one is they're like KB, the amount by which KB is increasing is exactly equal to the amount by which Ali is decreasing. And there's various ways to make this plausible, but in all of the ways that I tried, to sort of think through why that's true, it seems like you could just apply that same idea to the whole thing. Anyways, and I'll explain a little bit more about how I think through this. So, in other words, what this is saying is that the total distance d plus L, that is equal to the same distance. Again, since we're increasing from 4 to 8 and decreasing from 4 to 0. This wouldn't work if it was increasing from 4 to 10. But since the amount of increase is equal to the amount of decrease here, what this is saying is that the total distance run by these two athletes for the first 30 minutes is going to be equal, in other words, d plus L is like the same as if somebody was running at 4 miles an hour for an hour long. Okay, but somebody running at 4 miles an hour for an hour long is exactly how far Todd ran. So in other words, what Todd runs is d plus L. The distance that Todd runs is d plus L. But that's also the distance that I ran. And this right here, 4, is half of the final velocity, and this is exactly the formula that we have here. Okay, so that's one way to look at it. Now, another way to kind of think through this, which is also kind of confusing, would be if we assume, let's assume, so we want to prove this thing for this whole interval here. If we assume it's true for half intervals, then we could also show it's true for the whole interval. So if we show that this principle here is true for 30-minute blocks, then it's also going to be true for a 60-minute block. And if it's true for 15-minute blocks, it'll be true for 30-minute blocks. And so if you kind of recurse this property down, you can kind of say, well, if it's true, for a block of a very small amount of time, 2 to the minus 500 or something, then it's going to be true for, that sort of will propagate up to being true for this whole interval here. Okay, but if it's down small enough, that's kind of like constant velocity, and then things like this are going to be true. Anyways, so that's one way to think about it that's maybe not very satisfying as well, unless you're kind of comfortable with thinking in this sort of recursive way. But maybe spend some time thinking about what I said if you want to. The way that I prefer to think about this, which maybe it's just because I don't know, do you guys remember that episode of The Office where Michael kidnaps the pizza delivery guy, and Jim is like, you can't kidnap the pizza delivery guy. And Michael says, I think you're overthinking this. And Jim says, I think you're underthinking this. Well, it's possible that I'm underthinking this. It's also possible that I'm just influenced, by several hundred years of mathematical development past what these guys were thinking about. So one way to express what this is, so the distance that you travel, so this is, even without referring to this, the distance that you travel is going to be equal to your average velocity times the time that you were moving. So is equal to the average velocity times TF for T final, assuming we're starting the timer at time T is equal to 0. Okay, well, why is that? Well, this is just the definition of average velocity, because the average velocity your average velocity is equal to the distance that you ran or went or whatever divided by the time. So the distance you rode, if you just rearrange this says the distance is equal to the average velocity times time. Now, to me, it seems obvious that if you are accelerating at a constant rate, then your average velocity is just going to be 1. If you start at 0 and increase at a constant rate, that your average velocity is just going to be equal to 1/2 times the final velocity. Okay, and you know, in terms of like defining what the average value of a function is, we know this is absolutely true, because the average value, if we obviously they don't really have the notation that we're about to use, or the notions that we're about to use even, the average velocity, if you go over 1 unit of time, is with the constant acceleration is going to be a times t, and we're going from 0 to t. So the average velocity is going to be like that. And so now, what do we get here? Well, when we integrate this, we're going to get a t squared divided by t, divided by 1/2 2, and then multiplied by this t, and this is equal to a t divided by 2, which is 1/2 a times t, and that is the final velocity that we have there. Okay, so in terms of integrals, this is absolutely true. How would you argue for that without using integrals? Well, obviously that's not a tool that they have then. So, but again, in my opinion, there's no bigger leap here than what we did, than what I saw, than what I displayed before, than what I showed before. Okay. Anyways, this is clearly something that's true. If we are accelerating at a constant rate, then your average velocity is equal to 1/2 of your final velocity. And so the distance that you ran is going to be equal to the same distance that you would have run if you were going half of your ending velocity. Okay, in other words, your average velocity. Okay, so that's all I want to say about this. I will work through some more of these sort of kinematics questions that were motivating a lot of the mathematics. And if you remember from your calculus class, probably a lot of these sort of kinematics and physical things were motivating for your definition of derivative. One common way to define a derivative is to motivate the definition of a derivative, I guess, is to think about it as instantaneous rate of change. Now, these are things that the mathematicians back then and the physicists back then were only sort of beginning to talk about, like instantaneous velocity and things like that. And we'll look at some of the mathematics that more developed, especially coming up after spring break as a result of that.